Hello, everyone. Welcome back to this online class. Today, we are going to look at Newton's divided difference interpolation technique. Now, we have this question to answer. We are asked to discuss the Newton's divided difference interpolation technique and hence work out the following questions. Number one, use Newton's divided difference technique to determine the interpolating polynomial for a function f of x given the data below. So we have the table of x versus f of x. Hence, estimate the values of f of 0, f of 1.5, and f of 0.5. So first of all, let's derive the formula for the Newton's divided difference interpolating polynomial. Once we have found it, we'll use it on the data that is given, and then use it to approximate the values of f when x is 0, when x is 1.5, and when x is negative 0.5. So the polynomial takes the form, so write the Newton's divided difference interpolating polynomial, that's an abbreviation, takes the general form it's usually a polynomial of this form, Pn of x, remember it must be of degree n, is equals to b naught plus b1 times x minus x naught plus b2 times x minus x naught, x minus x1, x minus x1. Then you proceed in that manner up to the last one. There are so many other terms. Up to the last one is plus bn x minus x naught, x minus x1. There are so many other multiplications in between. Up to the last one, x minus x, n minus 1. So we need a polynomial of this form. This b naught, b1, b2, all the way up to bn, these are constants to be determined. So you can say where, and use another color, you write where b naught, b1, b2, all the way up to bn are constants to be determined. I'll tell you how to determine those constants from the given general form of our interpolating polynomial. Now, we said an interpolating polynomial must satisfy this condition. So you can write since, you write here, since Pn of x is an interpolating polynomial, since it is an interpolating polynomial, it must satisfy these conditions. The first one, of course, we know that it must be the same as f of x at the tabulated points. So what we mean is that Pn of x naught must be equal to f of x naught. Pn of x1 must be equal to f of x1. Pn of x2 must be equal to f of x2, etc. up to Pn of xn must be equal to f of xn. Now we need to determine the values of the constants b0, b1, b2, all the way up to bn. So you can write to find b0, what do? We need to put x is equals to x0 in equation. Of course, our interpolating polynomial, let's call it equation star. It is this one here. That is our interpolating polynomial. So I want to substitute where there is x, I want to replace that by x0 so that we see what we are going to get. So when I substitute x0 in equation star, what will we get? It will be Pn of x0 is equals to b0. The rest are zeros because you see here x0 minus x0 will be 0. Let me say just b1 into x0 minus x0, that is 0, plus b2 into x0 minus x0, x0 minus x1, then plus so many other terms, plus bn, x0 minus x0, x0 minus x1, times so many of them, x0 minus xn minus 1. So where we have x0 minus another x0, this will be zeros because of x0 minus x0. When this term will vanish, the other terms will vanish except the first term. So we say therefore, where we have b0, it is the same as Pn of x0. But what did we say is Pn of x0? It is the same as f0. So this will be equal to f0 or f of x0. So that is the value of b0. So you can say that b0 is equals to f of x0. Let us bracket this. Now we still need to find b1, b2, etc. Let's see how to find b1. So you can write here that to find b1, what do we need to do? We are going to substitute x is equals to x1 in equation star. So you write put x is equals to x1 in equation star. So when you substitute, what will you get? Let's see. It will now be Pn of x1 is equals to b0 plus b1 x1 minus x0 plus b2 x1 minus x0 x1 minus x1 plus so many of them up to bn x1 minus x0 x1 minus x1 times x1 minus xn minus 1. So where we have x1 minus x1, of course, that will be 0. So this term will vanish, and all those other terms will vanish. And we know b0. Instead of b0, that is the same as f of x0. So I'm going to replace this by f of x0. So this is f of x naught. And what about Pn of x1? We said that is the same as f of x1. F of x1. You can see it from here. Pn of x1 is equals to f of x1. So let me now make b1 the subject. So we can just say that therefore b1 into x1 minus x naught is the same as f of x1 minus f of x naught. This implies that b1 is equals to f of x1 minus f of x naught, everything divided by x1 minus x naught. And this you can write as, the abbreviation for this is the same as f, then this close bracket, x naught, comma, x1. That's how we abbreviate it. So that's the value of b1. Let's see whether we can find b2. And once you find the value of b2, it will be easy now to look at the pattern and deduce the values of b3 all the way up to bn. So again, you write to find b2. To find b2, what do we need to do? We now substitute x is equals to x2. So you write put x is equals to x2 in equation star. In equation star. So this is what you are going to get. Pn of x2 is equals to b naught plus b1 x minus x. No, we are not putting x to be x2. So this will now be x2 minus x naught. Then plus b2 x2 minus x1. That should be x naught. Then x2 minus x1. Remember the other terms will be zeros because there will be x2 minus x2 somewhere. Let's say if we have b3, b3 will be x2 minus x naught, x2 minus x1, x2 minus x2. That is 0 plus the other terms will also be zeros. So I don't even need b3 going on once. I only need up to b2. Why am I saying 0? Because it's x2 minus x2. That is 0, and 0 times any other value is 0. So we can now make b2 the subject. Remember, we know the value of b naught to be f of x naught. We also know the value of Pn of x2. This value is f of x2. I've already explained it up here. Let me take you back. It is this one here. Pn of x2 must be equal to f of x2. So I want us to make b2 the subject. Remember, we also know b1. The value of b1 is known to be, let's see, blue. b1, we already found it to be f of x naught, comma, x1. So with this, we can now be able to find b2. So you can say that therefore, I want to make it the subject. So b2 will be equal to f of x2 minus f of x naught minus f x naught x1 times x2 minus x naught. We are dividing by the coefficient of b2, so everything here divided by x2 minus x naught, x2 minus x1. Now we need to simplify. Remember, this can as well be written as, I can write in the next line. So this you can as well write as f of x2 minus f of x1. I'm introducing f of x1, then we also add f of x1. I have not changed anything. Add and subtract the same value. Then minus f of x naught. Now, what is the value of f x naught x1? We got it. That was our b1, which we said is the same as, look at it. When we write f x naught x1 is the same as f of x1 minus f of x naught over x1 minus x naught. So I'm going to replace by its value, or simply another expression for the same is because it is minus f of x1 minus f of x naught, everything divided by x1 minus x naught. This is times x2 minus x naught. And so the whole of this should be divided by, you divide this by, remember this is bracket, you divide this by x2 minus x naught times x2 minus x1. We can simplify this further. This can as well be written as f of x2 minus f of x1 over x2 minus x1, then minus f of x1 minus f of x naught over x1 minus x naught. Then everything here, this is numerator. So we divide this by x2 minus x naught. Remember, I've just rearranged it so that we have what we have in the numerator. You'll check that later, but you get what I've written down there. And so what is the interpretation of f of x2 minus f of x1 over x2 minus x1? Our interpretation for this one, let me take it. The whole of this, the first term, is the same as f, then x1, x2. The other term in the numerator will be written as f x naught x1. Denominator is just the same, so that is x2 minus x naught. And so how else can you write this? This is the same as writing, f x naught x1, x2. So we can say that therefore B2 is equals to f of x0, comma, x1, comma, x2. And so you can proceed with the same pattern to get B3 all the way up to Bn. So you can say that therefore, on replacing the constant in equation star, the Newton's divided difference interpolation or simply interpolating polynomial will take this form. We simply need to substitute those constants. So you can say, of course, even before we substitute, I can just tell you how to get, so that you can just say in general, or simply, similarly, your B3 will be equal to f of x naught, x1, x2, x3. Your B4 will be equal to f x naught, x1, x2, x3, x4 in that order. So we proceed in that order, etc. So now that we know how to find the constants in our polynomial, you substitute them back and then you get your interpolating polynomial. So something that is also very important is that you need to know how to find those f of x naught, x1, x2, f of x naught, x1, x2, x3, x4, etc. from the divided difference table. Now, you write a note, NB, and on this note, we are going to write that the constants that is B1, B2, well, let me start with B0, B0, B1, B2, etc. are easily obtained by constructing a divided difference table. Are easily obtained by constructing a divided difference table. As shown. So let's construct a divided difference table, and then I tell you how to get those constants from your table. So our table should look like this. We need to have x, then f of x, f of x, something like this. So that, let's say here we have x naught. I can use another color. Let's say here we have x naught, and here it is f of x naught, x1, f of x1, x2, f of x2, x3, f of x3. So that is our table. I want to show you how to find those differences. The divided differences. So this is what you're going to do. You'll take f1, f of x1 minus f of x naught, so that we get the first order difference of f, written as df. Of course, the divided difference, first order divided difference. So here we are going to write, let me use this, we write f of x1. I'll write it because I'm going to divide. So let me write it here. F of x1 minus f of x naught. And then you must divide by x1 minus x naught, their corresponding x values. So that is x1 minus x naught. And my question is, what was this? How can this be written? This is the same as f x naught x1, which we said is the same as b1. Because I'm going to tell you that later. Again, this other one, take f of x2 minus f of x1. You have to divide by x2 minus x1. x2 minus x1. Similarly, we'll have f of x3 minus f of x2 divided by x3 minus x2. So what is the abbreviation for all the, how do we write this? It's the same as f x1 x2. This also can be written as f x2 comma x3. We go to the second order divided differences. You take this minus this. That will be f x1 x2 minus f x naught x1 divided by, now it is this value x2 minus x naught. The extreme values are x2, then minus x naught. And so this is the same as writing f x naught x1 x2. Similarly, we subtract these other two so that we have f of x2 x3 minus f of x1 x2. What are the extreme x values? You subtract them, so it will be x3 minus x1. And how else can you write this? It's the same as writing f of x1 x2 x3. And finally, the third order divided differences, that will be equal to, just subtract the two, we'll have f of x1 x2 x3 minus f of x naught x1 x2 divided by the difference of the extreme x values, that is x3 minus x naught. And how else can you write this? It is the same as, that will be equal to f of x naught x1 x2 x3. So that is our divided difference table. So let me show you how to read those values. I can use another color here, different from the ones that have in the table. Let's use green. So what is the value of f of x naught? F of x naught here, we say that the same as b naught. So this is b naught. What about this other one? This is the same as b1. This other one is the same as b2. And so you proceed in that manner. This other value here is the same as b3, etc. So when you have a higher order differences, you can go to b4, b5, etc. So this is how you are going to read them along this kind of a line, sloping downwards in this manner, so that you start from f of x naught, that will be your b naught. So you go all the way up to the last one in that order. So having shown you how to derive the divided difference interpolating polynomial, because Newton's divided difference interpolating polynomial, and how to get the constants from the table, let us look at the question that you are given. Let me take you back to the question. We had this kind of a table. Let me take you back. Look at our table x versus f of x. So we are going to construct a divided difference table for this data. And once we come up with the polynomial, the interpolating polynomial, then I'll show you how to use it to predict or simply to estimate the values of f of 0, f of 1.5, and also f of negative 0.5. So let's construct the divided difference table for the data. So I'll go down. So we need to construct the divided difference table for the given data. And so look at our data. We are starting with 1 as the value of x. Then f of x is 24. So 1, 24. When x is negative 1, f of x should be 0. We have 260, 3, 120. Something you need to take note of about this divided difference interpolating polynomial, that your data, you don't need to sort the data in ascending order. And even the difference, the spacing between the x values need not be a constant or need not be uniform. That's very important. So it means divided difference is better than even backward difference and forward difference interpolating polynomials. Because in the backward difference interpolating polynomial and forward difference interpolating polynomial, you require that the spacing between the x values must be uniform. Here, there's no need. You don't even have to sort your data in any order. So let's get the differences. So we are going to start with the first order divided difference that is written as df. Remember, just subtracting as usual. So I'll use another color here. So it's 24 minus 0 over negative 1 minus 1. You can work out that 24 minus 0 over negative 1 minus 1. That should be negative 12. Is it negative 12? Oh, no, it's 0 minus 24. Let me change it. Should be 0 minus 24, not the other way around. so that our answer should be positive 12. So take note, it should be 0 minus 24. So this answer will be 12. Now, 60 minus 0 over 2 minus negative 1. Minus minus will be a plus. So that's 60 over 3, which will give you 20. We proceed to 120 minus 60 over 3 minus 2. And so that should give us 60. Those are the first order differences, of course, divided differences. Let's get the second order divided differences. You write d squared f. That will be 20 minus 12 over the extreme x values is 2 and 1. Take note of that. So that will be 2 minus 1. And this will give us 8 over 1, which is simply 8. The other one is 60 minus 20. The extreme x values are 3 and negative 1, so 3 minus negative 1, so that will be 4. 40 over 4, that should give us 10. And finally, the third order divided difference, 10 minus 8. Extreme x values will be 3 and 1, so that is 3 minus 1. And so that is 2 over 2, and the result here is 1. Having constructed this table, we can now be able to get the values of B1, B2, B0, and even B3. So this is B1, this is B2, no, this is B0, B1, these are the values B2, and lastly this one is B3. Remember how to read it along a line that is sloping in this manner. Your line must slope in this manner so that you start from B0, B1, B2, B3. This is our X0. That is X0. So it means if that is X0, then this is X1. This other one is X2. And this other one is X3. So let me bracket them. So those are the things you need from the table. Now, let's come up with a polynomial now that we know those constants. So our polynomial, the interpolating polynomial, must be a polynomial of degree 3. So you can write the interpolating polynomial must be of degree 3. So degree 3 because when you do the subtractions, we go up to the third order divided difference column. So our polynomial cannot be over degree greater than 3 because the last value there is d cubed of f. We're simply operating on f. So that kind of a polynomial of degree 3 is written as P3 of x is equals to B0 plus B1 x minus x0 continue adding all the way up to B3. So that is the polynomial. Now we need to replace the values of the constants and even the x0, x1, all the way up to x3. So when I replace, this is what I'm going to get. Let me return the same color. So this should give us, instead of B0, I'm going to write 24. 24. Replace everything. So we go to B1 and even the x's. So the value of B1, that was 12. So we are going to add 12. Then I don't know x, but I know x not to be 1. Our B2 is 8. X minus 1. Then x minus x1, there was negative 1. That would be x plus 1. Our B3 is 1. This is x minus x0. Our x0 is 1. X minus x1 is negative 1. X minus x2 is 2. So this you can as well write as 24 plus 12 into x minus 1 plus 8 into x minus 1, x plus 1 plus x minus 1, x plus 1, x minus 2. And so I know you can be able to open those brackets. You expand that and then you simplify, which you can be able to do, so that you get your interpolating polynomial as x cubed. It will be x cubed plus 6x squared plus 11x plus 6. So that is the interpolating polynomial of degree 3. So we can just say that therefore, P3 of x is equal to x cubed plus 6x squared plus 11x plus 6. Our interpolating polynomial of degree 3. Now let's use this polynomial to answer those questions. The first one, we need to estimate number 1, f of 0. This is approximately equal to P3 when x is 0. And so that will give us 0 cubed plus 6 times 0 squared plus 11 times 0 plus 6, and that is equals to 6. F of 0 is 6. What about f of 1.5? So number 2, you write f of 1.5 is approximately equal to P3 of 1.5. And so that is 1.5 cubed plus 6 times 1.5 squared plus 11 times 1.5 plus 6. What should that give us? You can press in your calculator. That should give you 39.375. 39.375. Another one is f of 0.5. This is approximately equal to P3 of it was negative 0.5, so let me change this. Should be f of negative 0.5, negative 0.5, approximate equal to P3 of negative 0.5. And so again, replace x with 0.5. That should give us, I said with negative 0.5, so that's negative 0.5 cubed plus 6 times negative 0.5 squared plus 11 times negative 0.5 plus 6. And so this should give us 1.875. 1.875. So that's how to use Newton's divided difference interpolation technique to be able to come up with an interpolating polynomial and also estimate some values of f of x at non-tabulated points between the tabulated x values. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When you meet next time, we look at more problems involving Newton's divided difference interpolation technique. Bye-bye.